classical physics is a simplification of quantum mechanics, just applied to macroscopic objects. All right, what else did we say about quantum?
Matter has wave-particle duality.
Yeah, the wave-particle duality, we talked about that. It's good. What was the equation that went with wave-particle duality? What was that equation called? De Broglie equation. You don't have to memorize it.
The what?
The wave-particle duality of matter, you know, and then we had the de Broglie equation. And what else? What else did we have? The Heisenberg uncertainty principle. So just tell me what the Heisenberg uncertainty principle is.
Well, yeah, their position is uncertain, but momentum is.
Okay. But you can't know both simultaneously, right, with high precision. And so those are what they call the two ideas leading to a new quantum mechanics, right? What are the two ideas? De Broglie and Heisenberg, wave-particle duality. So here's the wave properties of electron diffraction here. Here's the de Broglie wavelength, h over m. I use v for velocity. Your book uses u here for velocity, which is fine. U is used for the gases. And then the famous uncertainty principle, the Heisenberg uncertainty principle. And that pretty much shapes the way we think about electrons here. And so we put all those factors into what was that called? The equation, the equation at the base of quantum mechanics? The Schrodinger equation. And so we take into account the wave properties. We're talking about constructive interference and destructive interference, right? I tried to draw these figures here. We talked about particle in a box, scanning waves like this, or quantized. This is the wave function. Okay, let's continue here. Continue. This is the Schrodinger equation here. This whole thing is abbreviated H with a hat on it. H psi equals E psi. And so I gave you a simplified version of the Schrodinger equation. And what the answers tell us, what do the answers tell us to the Schrodinger equation? What are the answers in the Schrodinger equation? The wave function, the psi, and the psi tells us psi tells us everything. Basically, the psi tells us the allowed states for an electron in that atom. And so this is for the hydrogen atom. Psi, how many answers are there? How many allowed states are there? Infinite. So it's hard. Is it impossible to determine all of them? No. It turns out it's not hard to determine all of them because there's a pattern. And that mathematical pattern is given by these variables called quantum numbers. So when we look at the psi itself, the psi is an equation, a mathematical equation that has n, l, and m incorporated into it. And there are certain values of n, l, and m that will satisfy the equation so that the Schrodinger equation is valid. Okay, so here, these are the restrictions on n. If we know the pattern of n, l, and m, you know, m depends on l. M is for specific L. So whichever L we're dealing with, then we know it goes from minus L to plus L. So we determine it for each L. So we can call it M sub L. And based on those, we can figure out all the allowed states. And then we can look at what they mean. For example, here. Go a little farther. In interpretation, skip all this math. this is basically what it means. So here's a wave function here in a 3D plot. You can see here. This is positive amplitude, this wave function. Okay, then here it's hard to see, but underneath there's dots. Can you see the dots? And so we have the electron cloud, and then we have the contours here. You know, we have here's the 95% contour. Actually, did they use the 95%? Sorry, they used the 95% contour, correction, in the notes. The 95% contour is given by this here.
It's 95% of 90.
Not 90%. I was mistaken. 95%. I was pretty sure it was 90%. But. So this is the 1, 0, 0 allowed state. And so what do you see when you see this? Well, what you see is, you know, the electron has a 95% probability of being contained within the sphere here. And that's going to give it the lowest possible energy. Right? And so we see this as the 95%. Can we pinpoint the electron? Not really. We're just given this probability. I mean, it's here, it's somewhere in there with 95% probability. Do we pinpoint the energy? Yes, the energy of this electron here is minus 2.179 times 10 to the minus 18 joules, the electron being attached to the atom. And so our visualization is, okay, this is the lowest energy orbital. We call this an orbital, and the orbital just says, you know, we have high probability of finding an electron here, but what's the probability of finding an electron here, 35 picometers out? Very, very small, you know. And so it's pretty unlikely, because that remaining 5% is distributed between 30, let's say 35 picometers and infinity distance.
And you had talked about node.
A node, yes.
How's that? Does that mean like zero possibility to find?
Yes, right. So here we could see we're talking about nodes. Did I talk about the 2s orbital at the end? Yeah. Okay. Briefly. Well, the 2s orbital is going to have a node, and so the 2s orbital looks like this. You know, when we look at the wave function, it's a wave function here. Did I draw the wave function for 2s orbital? No, I didn't. All right, let's draw the wave function.
So 1s orbital doesn't have node.
The 1s orbital has a node. All orbitals have one node. You know what the node is? At infinity. R equals infinity. But so we ignore that node, and then we talk about internal nodes. And so the 1s orbital has no internal nodes. That's what he's saying. The 2s orbital has one internal node. And the node, if we look at the wave function of the 2s wave function, just on a 2D plot here, look like this. This is psi. What do we do with psi, though? So here's our wave function. If you look at our wave function, over here we have we call positive amplitude. Positive amplitude. Down here we have negative amplitude of the wave. You know, waves can have positive amplitude, negative amplitude. And so this is positive amplitude, negative amplitude. This is psi here. Okay, what we do with psi, though, is we, to get the probability, can you have a negative probability? Does that make any sense? No. So negative probabilities don't make any sense. So what we're going to do with psi is we're going to square it. And then psi squared is going to be related to the probability here. But when we square it, we don't want to lose sight of what amplitude the wave was. And so here, what was positive amplitude stays as positive amplitude, but now what was negative amplitude jumps up to positive. What's that?
Is that for 1s?
No, this is for 2s.
Oh.
This is the 2s orbital. This is, in other words, the psi 200 orbital. And what we do here is we label it. And so the color coding system is like this. You know, positive amplitude is red, and negative amplitude, or what was originally negative amplitude, is purple. In this case, it doesn't matter, blue or whatever, different color, or just write negative. Negative. And so you can see the color coding here. You know, this is the positive amplitude part. This is the negative amplitude part. It's color coded like this. And between the positive and the negative amplitude is what we call a node. The node is right here, where we have 0 amplitude. In terms of probability, there's 0 amplitude there as well. 0 squared is 0. And therefore, at the node, we have 0 probability of finding an electron. And so this is called the nodal region here, 0 probability of finding an electron. Here. In the space between the positive amplitude and the negative amplitude. It's a nodal. This is a nodal sphere, call it. We have nodal spheres and nodal planes. So this is a nodal sphere. And so how does an electron get across? Well, if an electron is a wave, then it makes sense. You know, waves can... Did I draw the wave like a sine wave? You know, waves
Yes.
like this can have nodes. And so if you think of this as being a wave, then yeah, waves can have nodes. Or the electron is a wave. And so anyway, this is the psi 200. Actually, let's take a look at the psi 300 here. The psi 300 is called the 3s orbital. Let me erase this here. But the 300 has how many nodes? 2. So we have positive amplitude going to negative amplitude, going to positive amplitude, going out to infinity. We square it. The reason why we have to color code this is we don't want to lose the phase information. You know, this positive, negative, positive is called the phase of the wave. And so it's like this, you know, the square root of 4. Is the square root of 4 plus 2 or minus 2? Well, you lost the phase information, so we don't know what it was. It could have been plus 2 squared, or it could have been minus 2 squared. Sometimes we need to know the answer to that because that's important for us. And so why is it important for us? You know, why don't we just take it as 4, you know, plus or minus 2? Well, it's because of how waves add up, you know. If you got negative amplitude interacting with positive amplitude, is that favorable or is that destructive? It's destructive. You want negative amplitude with negative amplitude or positive amplitude with positive amplitude. That's constructive. And so this is important, this phase information, when we try to form bonds. You know, there are only certain kinds of bonds that, I mean, there are certain rules that govern this that we got to be aware of. And so anyway, this is the phase information. For us, are we going to use it? Not really. We aren't going to get in that deep, you know, in that deep to have to use it. But, you know, just to get you started, they're starting to color code these. Are you going to have to memorize the color codes and positive amplitude, negative? No. In fact, you're just okay. You're okay with just forgetting about this as well. You don't really have to know this. But it's good for your future class to know. So anyway, there are certain things you might notice. Now, one thing is you might notice a pattern with the nodes. Is there a mathematical pattern for the nodes that we could call the law of the nodes? Yes. That would be called the law of nodes. The number of nodes is equal to n minus 1. So if n was 1, we had 0 nodes. If n is 2, we have 1 node. If n is 3, we have 2 nodes. This is a consistent pattern, and so we could call it a law, the number of nodes. There are, actually, let's talk about, we need to talk about this in a little bit more detail. There are more orbitals when n is equal to 2. Did I write them down? When n is equal to 2, L could be equal to 0, and m is equal to 0, and then we have the psi 2, 0, 0, which is the 2s orbital, we call it, the one we just looked at. When n is equal to 2, we could also have L equal to 1. If L equals 1, then we go from minus 1 through 0 to plus 1. And so we have 3 orbitals, 2, 1, negative 1, psi 2, 1, 0, and psi 2, 1, 1. These are called the 2p orbitals, and there are 3 of them. And so when I look at the wave function for the 2p, I'll look at a 3-dimensional coordinate system like this. And so taking a look at the wave function, maybe one of them will look like this. Got positive and negative amplitude like that. And so I have a wave function that goes along the x, and I'm going to have a wave function that goes along the y as well. Oops. Let's try to draw that a little bit better. So we got positive, we got negative amplitude here. And then we're going to have a wave function along the z. So coming out like this. We got positive like this. And so we got these wave functions that are overlapped. When I square them, I'm going to get these. And so we'll just do the 95% boundary here, looking at these orbitals. When I do the 95% boundary, this is what I get here. This is the PZ orbital in 2D. Here we can see this is the positive, this is the negative. Both of these are representations of that. Actually, this is more accurate. And so the orbitals that result from this, show that. Are interesting because they have this. You guys are familiar with the p orbitals already? The p orbitals. The p orbitals have this kind of figure 8 dumbbell shape, yeah. And so this is one orbital, and this one orbital is going to have 2 areas where we're going to see high probability, and it's not right at the nucleus. The highest probability is going to be about here and here. Not right at the nucleus. In fact, right at the nucleus, we have a node. This node is called a planar node here, versus the s orbital had a spherical node. And so this is a 2p. This would be the 2p. This is an xy plane, so this is the 2py orbital. And so what we see here is that this, the m value, psi 2, 1, negative 1, psi 2, 1, 0, and psi 2, 1, 1. The m value, there are 3 m values. 3 m values means that the number of orbitals equals 3. And so the m tells us the number of orbitals, and each one has an orientation. For example, one of these, and actually I need to go back and check, I think the negative one is a PZ. But nonetheless, it depends on how we define the coordinate system. And so once you define it, then it sets it. But I'm just going to use this. You know, one of these is px, the other is a py, and the last is a pz. I think it was pz, py, px. But I need to go back and look at that.
What did you say about like if it's like how it's closer together? What does that mean at the bottom? Or like in
Here?
between?
Yeah, the higher density of lines means just higher probability. It's hard to see, but there are dots here underneath this. And the greater the density of the dots, the higher the probability. You can see that also, the higher this peak, the greater the probability is. And so this is just telling you, when an electron in this orbital has an energy and the probability, that is where its position is somewhere around here. And so 3M values and orientation, 3 orientations. Yeah, when we square it, the negative amplitude, you know, it was probably, let's look at this one. You know, it was probably the wave function like this. There was a positive part of the wave, a negative part of the wave. When we square it, we lose that phase information. And so when we square it, we color code the orbitals. So this was the positive part of the wave that was squared. This is the negative part. The negative part turns positive when we do the probability. And so we just color code it to make sure we don't lose the phase information. And that's it. So what do the p orbitals look like, the 3 of them? This is what they look like. They look exactly the same. The only difference between these 3 orbitals is the orientation. So the px is aligned on the x-axis, the py along the y, and the pz along the z. We've got these 3 orbitals. These are called energetically degenerate. Degenerate orbitals. Degenerate just means they're the same energy. Degenerate orbitals, same energy. All right, once we look, we did L equals 0, we did L equals 1. Is there an L equals 2 allowed? For n equals 2. N equals 2, L equals 2 is not allowed, forbidden. And so we have to jump up to the next n. The next n would be n equals 3. So let's talk about n equals 3. I'm going to come back to these orbitals in a second. But when n equals 3, what are the allowed orbitals? So if n equals 3, then we have L equals 0, M equals 0. That means we have the psi 3, 0, 0. This is called the 3s orbital. 3s orbital, this is spherical. The only difference is how many nodes will this have? It's big. You know, it's a lot bigger than a 1s orbital, and it's going to have 2 nodes. So there's a node here and a node here. And so we can look at how the amplitude of the wave function changes. You know, positive to negative to positive. Yeah. So this is a 3s with 2 nodes, and then this would be the 95% boundary. Compared to 1s, a 1s orbital is going to be quite a bit smaller than a 3s orbital. And a 1s orbital is going to have lower energy. You expect a higher energy orbital, the electron could be further away from the nucleus, right? It has more energy to travel or escape the pull of the nucleus. And so 3s orbital, higher energy. All right, then we have the L equals 1. If L equals 1, then M varies from -1 through 0 through +1. And so we got the psi 3, 1, -1, psi 3, 1, 0, psi 3, 1, 1. And these we call the 2p orbitals. There are 3 2p orbitals with different orientations. We have the px, the py, and the pz. The difference between these p orbitals and the previous p orbitals, one, they're bigger. are a lot bigger than the 2p orbitals. And 2, they're going to have not just one node, they're going to have 2 nodes. But the 2 nodes are going to be kind of odd looking. And so let's take a look at one of the p orbitals, like this. And if we look at it, it's going to look something like this, where we have it's kind of the dumbbell shape again, right? Except we have to cut it with another node. And so there's going to be one node here, which we call a planar node. This is a nodal plane. Oops. Nodal plane. And then there's another node here, like this, which is called a spherical node.
This is 3P, not 2.
Yes. Sorry, this is 3p. 3p. And so this would be the 3p, what is this one? 3pz? No, at y, 3py. This would be the 3py here. And so it just looks a little different. Okay, then if L equals 0, then we have L equals 1. And then finally, we can have L equals 2. So let's take a look at L equals 2. A 2p orbital is going to be quite a bit smaller. And so L equals 2, then M equals minus 2 to plus 2, going through 0. So minus 2, minus 1, 0, plus 1, plus 2. And so we have 5 possibilities. We have the psi 3, 2, minus 2, psi 3, 2, minus 1, psi 3, 2, 0, psi 3, 2, 1, and the psi 3, 2, 2. And so this means there's 5 m values, meaning that there are 5 orbitals that are degenerate. In other words, this is called a sub-level. 5 orbitals, 5 m values, 5 orbitals in the D, we call it the D sublevel. Sublevel has another name. It's also called a subshell. These 3 orbitals here, the 3, 1, minus 1, 3, 1, 0, 3, 1, 1, is the 3p subshell or sublevel. So what are the 5 orbitals in the D subshell? These are the 5 here. And if you look at the nodes, take a look. At the nodes. I guess I'm already down here. They have 4 lobes. D orbitals have 4 lobes. And 2 nodes. And so there's a nodal plane here and a nodal plane here. 4 lobes. This is 1 orbital. This orbital is called the dx squared minus y squared. It's on the x and the y axis. This orbital, take a look at the lobes. The lobes are between the axes. We call this the dxy because it's in the xy plane, as far as the orientation goes. The orientation, you could either use this code, you know, the m value, but each m value codes for one of these. Then we have the dxz along the xz plane, the dyz, and this is called the dz squared. And so all these 4 look exactly the same, they're just oriented differently in space. This one is different. This one doesn't have 2 planar nodes. This one has 2, not spherical, 2
Planar.
conical nodes. There's a node here. This is a node here. And so these are my 2 conical nodes.
like an ice cream cone.
Do we have to know like the difference between all of them?
No, you don't have to know. In fact, all I'm going to ask you is how many nodes. And so there you just memorize the law of the nodes. The law of the nodes is n minus 1. It's easy. I'm not going to ask you spherical or conical or anything like that. Uh-huh.
Can you say how many nodes are there for d orbital?
For d orbital?
The two of them.
No, it depends on n.
I mean, when n equals 3.
When n equals 3, then it's 2 nodes.
The law of the nodes.
It's the law of the nodes. 1, 2. You just slice it. That's a lot. I'd go like this. Tell me how many nodes I expect to find in an n equals 1,000. Let's say I'm looking at the 1,000th. There'd be 999. So you can imagine this being sliced and diced. 999 nodes means there's going to be a lot of lobes. Don't you think? A lot of lobes.
So is the number of possible orbitals equal to possible numbers of?
That's a good question. Do you see the pattern? When n equals 1, how many orbitals did we have? 1. When n equals 2, how many orbitals did we have? Not 2. We had 2 sublevels. When n equals 3, we have 3 sublevels. The S, the P, and the D sublevel, right? And so this would be the law of sublevels. The law of the sublevels, nobody calls it the law of the sublevels, I guess. People just know this. Is that n equals the number of sublevels. All right, what about the law of the number of orbitals? Because these are patterns you see, right? The law of the sublevels holds all the way to infinity. The law of the orbitals would be, what pattern do you see for the law of the orbitals? The number of orbitals for a given n is equal to?
Possible number of
No. That's true, the possible number of m values, but there's a simpler way of doing it. Is n squared. Right. And so the law of orbitals for a given n number of orbitals for given n is equal to n squared. And so if n is equal to 1, we found 1 orbital. If n equals 2, we found 4 orbitals total, an s orbital and 3 p orbitals. When n is equal to 2, 4. When n is equal to 3, 9 orbitals. What are they? 5 d's, 3 p's, and 1 s. That's 9 orbitals. N equals 5. How many orbitals?
25.
How many sublevels?
4.
How many nodes are those going to be? 4. And so there are going to be a lot of lobes, but you know when you there actually I was looking for a video this morning. It's disappeared, but this video shows some of the higher energy orbitals and all the crazy nodes they have. But it's disappeared, so I couldn't show you that video. Instead, I'm going to show these from the book. But it's okay. So you can see here the nodes. You see the planar nodes? Or just they drew one set here. Actually, they only drew one node here. All right, this is n. Actually, you can tell me. What do you think this is? N equals what? Let's see. This is, I got one node here and then one node here. This must be n equals 3. This is one orbital. There are 1, 2, 3, 4 lobes. This is a d orbital, right? Can you tell that's a d orbital? D orbitals typically have 4 lobes unless it's that conical one. But what d orbital is that? Is that n equals 4? You know, 1, 2, 3. 3 nodes. This is the 4dxy. This is the 3pz. All right. Now what we're going to do is we're going to try to put it all together and to map it out. And so when we map it out, we like to map it out in terms of an energy level diagram. Okay, from the Schrodinger equation, from quantum mechanics, the energy E sub n is equal to minus R sub h over n squared. And so the lowest energy orbital is going to be n equals 1, which is going to be minus 2.179 times 10 to the minus 18 joules. This is the psi 100. I'm just going to call it the 100 orbital. No, we'll drop the psi, or the 1s orbital. We have letter designations for this. The 1s, the 1 is for n. The s is for L. And so let's talk about the letter designation over here. If L equals 0, we give it the letter S. If L equals 1, it's called a P. If L equals 2, we call it a D. If L equals 3, we call it an F. If L equals 4, what do we call it? If L equals 4, it's called a G. 5, H. What do you think the rest are? What's the next? I. 6, etc. So this letter, you know, a lot of people think, okay, S stands for sphere, right? S stands for sphere because the s orbitals are spherical. But actually the s didn't come because, you know, P stands for what? No. These letter designations came from spectroscopy. And the reason why, you know, S stands for sharp. You know, because people saw a sharp line in the spectrum. That sharp line corresponded to S electrons. And then P standed for the principal. The principal line is the big one, you know, principal line in the spectrum. And D standed for diffuse. Diffuse line is this one that's kind of weak and spread out. It's the diffuse line. And so these letter designations come from the spectrum, you know, spectral origin. Not the shape of the orbital, but the shape of the peaks in the spectrum. And so that's why we have this sharp, principal, diffuse, and then it just goes, you know, alphabetical and beyond. Well, F, what does F stand for? Fundamental? I don't know. I forgot. A, B, C, D, E, F, G. No, F might have gone alphabetical from there. We aren't going to talk about the shapes of those lines, but we got the 1s. Then what comes next? Okay, we have the 200 or the 2s. And what's the energy of the 2s? It would be 1/4 my Rydberg, right? And then we have the 2p. The 2-1, -1. The 2-1, 0. And the 2-1-1. 2p. And so I got my 3 2p's. And it turns out that all these orbitals have the same energy. Oh, how can all of these orbitals have the same energy?
They're the same.
Same energy for one electron species. Same energy for the one electron species. And so let's talk about this. Why would those have the same energy?
The same orbital.
They're the same energy level.
Because
What do you think?
okay, the reason they have the same energy is because they have the same, what we call effective distance from the nucleus.
So they're the same energy level.
It turns out, if you look at an electron, the farther the electron gets from the nucleus, the higher energy it's got to have, right? That's the reason why. But how can they be the same effective distance? Because their shape is totally different. And so what it turns out is this. When we look at this here, we are going to look at something called the RDF or RPF. The RDF or RPF. RDF, RPF, what that stands for is radial distribution function or radial probability function. All right, let's take a look at a 2s orbital here. And there's going to be some node in here. This is going to be the 95% boundary. Where is the highest probability of finding the electron? Where is the highest probability?
Within
Right next to the nucleus, because when we look at the probability, actually, let's maybe I should put that up. Where's the highest probability? The highest probability is going to be at the peak of the chi-squared graph. And so I might not have a chi-squared graph. Let me just check. Grab one. Well, anyway, the highest probability, although I don't have the graph here, we'll just draw some dots representing it. It's hard to tell the probabilities looking at something like this. But when I look at something like this, here's the nucleus here. And so I look at the dot distribution. The highest probability is going to be where I'm going to see most dots or most of the contours, which is going to be near the center. And then we're going to have a node, and this outer shell is going to have much lower probability, like this. And so, in fact, do you see that there's overlap here between the 1s and the 2s? Where's the highest probability for the 1s? Right at the nucleus, right? The highest probability for the 1s is right at the nucleus. Where's the highest probability for the 2s? Right at the nucleus. Wait, aren't they occupying the same space then? They both have the highest probability right at the nucleus, so aren't they going to have the same energy? No, they aren't going to have the same energy. We're going to have to look at something else. We're going to have to look at, instead of the highest probability being the nucleus, we're going to have to look at the most probable distance the electron is from the nucleus. And so what is the most probable distance? The most probable distance is where we divide up this space around the nucleus into little onion type rings. You know, these would be of equal thickness. And so what we're going to do is we're going to divide the space up around the nucleus like this into hollow spheres of equal thickness. And then we're going to say which one of these hollow spheres will have the most dots. Will the one at the nucleus have the most dots? You would think, you know, the highest probability is right near the nucleus, but will the one at the nucleus have the most dots?
The dots represent.
It'll have the highest density of dots, the one at the nucleus, but there's a problem. Because the one at the nucleus is kind of small. It's kind of small. And so it turns out when I'm counting up the dots, even though out here, if you look out here, there isn't as high a density of dots, but there's a much larger volume. And that much larger volume can capture more dots. But, you know, if I go to the biggest volume way out here, you know, a concentric ring way out here is going to have the biggest volume, but there's no dots around here, right? And so what I need to do is I need to maximize two separate functions. I need to maximize the density of the dots and the volume of the dots. And so these are the two functions here. If I look at the density of the dots, well, that's what we call the psi squared. And so if I look at psi squared is going to have the highest probability right at the nucleus. It's going to drop down at the node and then bump back up, like that. Okay. Maybe I shouldn't have picked this. If I look at the volume of the spheres, the volume of the spheres is going to increase the further I go out. And so what I have to do is I have to maximize both these functions. When I maximize both these functions, then I get something like this. I get something called the most probable distance. You know, where the density of the dots have been maximized and the volumes have been maximized.
Is it where two
Intersect.
Pretty much, I think.
So is that what the radial distribution function?
Yes, that's what the radial distribution function is.
So we maximize. Can you repeat that again, please?
I'm sorry?
Can you repeat what we do?
Yeah, I am. I'm going to repeat it right now. Do you see what we're doing here? This is RDF. We're figuring out where's the maximum density of dots? Right near the center. But which of these rings will have the most dots?
The 40?
Maybe it looks like the 40, doesn't it? And so let's see what this one would look like in a plot. Just do this one as a plot. So I'm going to erase my previous plots. All right, and so what am I going to plot? One, I'm going to plot the the intensity or the density of the dots, that's my psi squared. And so let's go from here. I'll go from this is the nucleus here. And so the psi squared, I'm going to have the most black dots right at the center, and the black dots are going to drop off like this. So this is my psi squared. And then I'm going to plot the volume of these rings. And the volume of the rings is going to increase as we, or the area, I should say the area since this is just flat. So area of the ring increases. And so what I want to do is I want to find my most probable distance, which is going to be around here.
The interception.
Yeah. We'll do the most probable distance. It turns out for the 1s orbital, do you know what the most probable distance is?
53.
Yes. 53. 53 picometers. 5.3, or no, 0.53 angstroms. And so here, this is 53 picometers, 0.53 angstroms. Does that number sound familiar?
The rate.
This number sounds familiar because we saw it in the Bohr model. What was the first Bohr orbit? The radius of the first Bohr orbit? This is slow. Well, they don't say here specifically, but you know the first Bohr orbit is right here. This is the n equals 1, and the radius is a naught. You know what a naught is? 53 picometers. And so Bohr hit this as the first orbit, right? Well, it makes sense because if the effective distance, this is the most probable distance, so this is what I call the effective distance of the electron in a 1s orbital. If we could make that electron just stay in one place, then that one place would be 53 picometers from the nucleus. Sometimes it's super close, sometimes it's super far, but we kind of average that over a long period of time, we're going to get 53 picometers. And that's what dictates the energy here of this. Okay, almost done. Yeah. So do you know what we have here? These are RPDs. Oh, I forgot one more acronym. RPD. What did I have? I had RDF, RPD, I mean RP,
RPF.
RPF,
RPF.
RPD. You know what all these things stand for? The same thing. That's it. And so we have our radial probability distribution, our radial distribution function, our radial probability function. They're all the same. And what it tells us is because here we have our psi squared, right? This is our psi squared. And then here we have the volume. Something like that, the volume. And we try to
this is kind of compressed here, sorry, the volume, and we try to maximize, right? And when we maximize, we get the, what did I call it? Most probable distance, or the effective distance. The effective distance here would be 0.53 angstroms.
4 p.m.
Is it the same effective distance for all atoms, or just
No, it's just for hydrogen. This is
For
just for
hydrogen.
hydrogen.
So when you have like the same energy level for the two, n equals 2, that's for the hydrogen atom.
But okay, now this is the 2s, right? This is 2s just for hydrogen. For others, it's going to be different. But what about the 2p? Here's the 2p. Oh, actually, sorry, this is the 2s. That's the 1s. This is the 1s. Here. This is the 2s. You see the 2s is going to have a most probable distance a little above 5 here. Here's the 2p. The 2p has a most probable distance of below 5. And so when I think about the 2p is actually closer to the, effectively, it's closer to the nucleus. So if it's closer to the nucleus, it should be lower in energy, right? The closer it gets to the nucleus, the lower in energy it becomes. The farther it gets from the nucleus, the higher in energy it becomes. And so when I look at this, then the question comes about, why are these the same energy? They shouldn't be the same energy because they both have different effective distances from the nucleus. And so why are they the same energy? The same energy. Well, they're the same energy. Why? Because of this. This effective distance is over 3 dimensions in the sphere. Let's try to draw a sphere here. It's not very good. But here I have, let's say, 50. This is slightly greater than 5 picometers. But over here, this is what we call isotropic. You know what isotropic means? Isotropic means it's the same in all 3 dimensions. So no matter where I look, it's the same. 53 picometers, the electron's going to be out, right? Over here, this is what we call anisotropic. Anisotropic means if I'm sitting here at the center and I look out, it's not all the same, right? It's not all the same because here the electron's going to be closer, right? Effectively, it's going to be closer. And so here, let's say this is the effective distance here. It's going to be closer, but when I look out in this direction, do I see any electron? No. And so it's closer, but the volume of interaction is less. And so when I look at these, if I normalize this over all 3 dimensions, then the distance becomes the same as this. And so essentially what that boils down to is, yes, their most probable distances are different, but normalized, their effective distance is the same. 53 picometers, well, not 53, whatever it is here. 5 a little greater than 5 here. This normalized over 3 dimensions, you'd have to weaken the interaction to spread it out over these areas where there's no density, right, or very little density, and it would bring it above 5. Does that make sense?
So they're the same energy. They have the same energy.
They have the same energy because they both have the same effective distance, normalized over 3 dimensions. in an isotropic sense. Okay, so why are they the same energy? Because, somebody repeat it for me.
The
Because
effective distance are the same.
the effective distance is the same, normalized over. Yeah. Over 3Ds. That's why. And so they have the same energy. In fact, for the hydrogen atom, we can carry this out further. It stops. Okay, so this is our energy level diagram for the hydrogen atom. And so we have the first energy level, or what we call the first shell. We have the second shell. In the second shell, there are two subshells. There's a 2s subshell and the 2p subshell. The 2s and the 2p subshell have exactly the same energy because they have the same effective distance from the nucleus. And so they're going to be the same energy. In fact, this carries over to n equals 3. N equals 3 has three subshells, the 3s, the 3p, and the 3d. A total of 9 orbitals. And all 9 orbitals are going to have the same effective distance normalized over 3D. And so even though the shapes are totally different, you know, these 3D clover leaves versus the 3P dumbbells versus the S sphere, right? The effective distance is the same. Let's do one. Let's fill in the table some more. What comes after the n equals 3 shell? The n equals 4. How many orbitals in the n equals 4? 16 orbitals. And then after 4 comes 5. And the energies, you know, this is minus 2.179. Actually, let's just do Rydberg. Minus r sub h over 1 squared. The energy for the n equals 2 is minus r sub h over 2 squared, or 4. In other words, 1/4 r sub h. This is going to be 1/9 minus r sub h. This is going to be 1/16 minus r sub h. So what's happening is the energy levels are starting to compress. They're getting closer and closer in terms of spacing. And so let's go to n equals 5. N equals 5, we should be able to do that. Let's figure out all the subshells and all the orbitals in the n equals 5 for the hydrogen atom. And so let's try to do that quickly here. So I'm going to take the n equals 5. Let's blow that up and let's figure out all the orbitals in the n equals 5. So let's make some room right here. I'm going to write them in here. So the n equals 5 would be down here, a whole bunch of orbitals. In fact, how many orbitals? 25 orbitals. Let's figure them all out. What are they? Okay, we'll start it from the beginning. 5, 0, 0. This is called the 5s. And then the 5, 1, negative 1, 5, 1, 0, 5, 1, 1. These are the 5 P's. It's 4. And then the 5, 2, negative 2, 5, 2, negative 1, 5, 2, 0, 5, 2, 1, 5, 2, 2. These are the 5D. And then we have the 5, 3, negative 3, 5, 3, negative 2, 5, 3, negative 1, 5, 3, 0, 5, 3, 1, 5, 3, 2, 5, 3, 3.
How are you doing? How do you determine?
So you have to
Following the rules. For each L, there are minus L to plus L. And so these are called the 5F. There's 7 of those. 7.
That's 7 orbitals, right?
Right. In fact, we can figure out, let's say, how many orbitals are in the 6I? And so this will be the law of orbitals in a sublevel. What is the law of orbitals? Law of number of orbitals in a sublevel, not in a level, in a sublevel or subshell. What is the law? Law of number of orbitals in a subshell. And so the 5D had 5, the 5P had 3, the 5S had 1, the 5F has 7. Do you see the mathematical pattern? No. Okay, this is L equals 0, L equals 1, L equals 2, L equals 3. Now do you see a pattern
Yeah,
related to L?
plus N.
2L plus 1, right, is equal to 2L plus 1. And so if I'm at L equals 100th, how many orbitals are there going to be in that 201? And so this is why I say it's easy to figure out all the orbitals up to infinity. It's not too difficult. In fact, this is L equals 4. So how many orbitals am I expecting? L equals 4. Yeah, 2 times 4 is 8, plus 1 is 9. I expect 9 orbitals in my 5, what do I call this? 5G. And so in the 5G subshell, or sublevel, I have 9 orbitals. What are they?
5, 4,
5, 4, negative 4, 5, 4, negative 3, 5, 4, negative 2. Adrian, you want to come up with this one? Adrian, yeah.
Names?
Yeah. Do you see the pattern?
4, 3, 2, so 5, 4, 1.
5, 4, negative 1.
Okay.
All right, somebody else. 5, 4, 0, 5, 4, 1,
Oh yeah.
5, 4, 2, 5, 4, 3, 5, 4, 4. And so those are my 9 5G orbitals. How about what comes after G? A, B, C, D, E, F, G, H. How about 5H? 5, 5, negative 5? No, not possible. These are forbidden. So I got to stop here and then go up 1.
Oh, because 5 came from.
And so, yeah, remember the lines? The red line was an electron in the 4th shell going to the, or no, the red line was in the 3rd shell going in the 2nd. The green line was an electron in the 4th going to the 2nd. This is the blue line in the hydrogen spectrum. The blue line is an electron in one of these orbitals here, dropping down to, from n equals 5 down to n equals 2, we get the blue line in the hydrogen emission spectrum. That's what we see. Now there are rules governing angular momentum rules. Not all, like for example, if it's in this orbital, not all transitions are allowed, but we aren't going to worry about that. Because of conservation of angular momentum, which L is the angular momentum quantum number. Okay, I'm going to stop here, and then we'll look at multi-electron atoms tomorrow.